Hello everyone, welcome to Chapter 16, Vodcast Part 1 of 2. This is going to cover Chapter 16, Sections 1 through 4, which includes a brief overview of acid-base theory, a little bit on how water plays a role in that, and of course the pH scale. Alright, get your guided notes and let's begin. So the first theory that we're going to talk about and discuss is the Boyle's theory of acids and bases. And if that name seems a little bit familiar, it should, because of Boyle's law from honors chemistry. It's a gas law. Anyway, in 1661, Robert Boyle summarized the properties and characteristics of acids as being the following. So acids have a sour taste, they're corrosive, they change color of certain vegetable dyes like litmus from blue to red. And he also noticed, and this is kind of where it evolves from, is that on certain fruits and vegetables and stuff, most fruits and vegetables, when they first start growing, they have a green color. And then as that fruit ripens, the fruit itself will actually change color. When you, for example, grab an apple that has not had enough time to ripen, it'll have a green color, and when you bite into it, it'll have a sour taste. But as that apple ripens, the acid that is inside of that apple will actually convert into sugar, and it'll turn sweet. And as that acid is converted into sugar, the color, the outside color of that skin, of the apple, changes. Well, if it's a red apple, it'll change to red. But anyway, acids, also he noticed that they lose their acidity when they're combined with something called alkalis. Now that word alkali should sound familiar for the periodic table, the two families, alkali and alkaline earth metals. Those metals on the periodic table are typically found within Earth's crust. And as different geological processes happen, specifically water, erosion with water, as water comes in contact with those metals, they turn into what we call metal hydroxides. Hydroxide, that word should sound somewhat familiar from maybe some of your previous history in chemistry. Anything that contains a hydroxide is typically basic. So we generalize basic compounds by calling them alkalis. All right, so just a little bit of history about that. Boyle also had some time to research a little bit about bases. He discovered that bases feel slippery, and they typically change color of litmus from red to blue. Alkalis become less alkaline when they combine with acids. So pretty much anything that has a slippery feel, kind of like soap, for example. Soap is slippery, and all soaps have some kind of basic characteristic to them. So from now on, the next time you're in the shower and you're soaping up, every time you feel a slippery substance within your fingertips, that's typically a base. So looking at these pictures and diagrams, there's many different ways that you can monitor the amount of acid or base that an object has. So there's this thing called a pH scale, and I hope that sounds familiar and that you're kind of familiar with that. But the pH scale typically runs from 1 to 14. And I know it's kind of hard to see it in the image here, but if something has a low pH, it is going to be acidic, an acid. And if something has a high pH, it's considered a base or basic. So we have, over on the left side here, we have two images, two different little beakers going on here. And on the far left-hand side, I find it funny that you can tell that this guy's not wearing any gloves, or whoever's taken this picture didn't wear gloves, and that's like a major no-no. But anyway, so the paper that he's holding on the far left image is starting off as a red color, and then as he dips it into that solution, it turns blue. So from now on, when you see, or if you think about the color blue, I want you to think blue for base, BB, blue base, basic blue. So the solution on the far left image is a base. The solution next over, he is holding a blue strip, and then as it's dipped down into the solution, it turns red. So when you think of an acid, I want you to think about the color red. There's a couple different ways that you can also track the strength of the acid or a base, and Probably from your biology class, you probably had some experience with some pH paper. pH paper is kind of fun. It's like a rainbow of different colors. Red still represents an acid, and the blue and sometimes purpley colors, those will represent your base. But in AP, we're probably going to be monitoring most of our pH with a pH meter. That gives you a numerical value for the pH concentration. So anyway, another way that we also monitor, and you guys have had a little bit of practice with this, is with various types of indicator. And you've done some titrations now, and I want you to understand that a titration, sometimes when you work with an acid and a base and you have equal parts of acid and base reacting, you're not always going to get a neutral solution at the end point, you know, where like exactly 1 mole of acid has reacted with exactly 1 mole of base. When you get to that middle point, you're not always going to have a perfectly neutral solution. But if you did, some of the indicators that would work really well are the indicators that change color around a pH of 7. So in this picture, I know it's kind of hard to see, but if we come straight down 7, there's a couple different indicators that might work for you. And these are kind of some of the more familiar ones that we work with. You've got phenol red and bromethymol blue. Those are the more familiar indicators that we typically use in most titrations. But as you can see, there are many different types of indicators that you can use depending on where you think your pH will be at the end of, or the end point, or the equivalence point of your titration. So obviously I've got to teach you a lot about those titrations, so let's get to it. A more refined definition of acids and bases came along around 1887. So this gentleman right here, he won a Nobel Prize in chemistry in 1903 for his discovery that when certain substances dissolve in water, specifically ionic compounds, they can conduct electricity, and he called those guys electrolytes. His name is Arrhenius. So he came up with a definition of an acid and a base, and it is the basic foundation here of the definition of an acid and a base. He said that an acid is any substance that dissolves in water to make these H+ ions, and that a base, when it dissolves in water, it has to make OH ions. And both acids and bases, they conduct electricity in water. Cool stuff. But Arrhenius' theory had several disadvantages. The biggest disadvantage is probably the fact that the solvent, whatever you dissolve the acid or the base into, does not play any role in Arrhenius' theory in the way that the acid behaves. So an acid is expected to be an acid in any solvent, right? So this was actually found not to be the case. And for example, hydrochloric acid happens to be fairly strong acid, but it also happens to be a highly polar compound, right on the cusp of, being, could it possibly be ionic? I mean, that's how strong it is. But hydrochloric acid does not dissolve in certain compounds like benzene. Benzene happens to be a non-polar organic compound. And so if you try to take hydrochloric acid and you try to push it into benzene, it will not dissolve, and it will not dissociate into its ions, into an H+ ion and a Cl ion. It doesn't want to do that. But we know that hydrochloric acid is a fairly strong acid. So the nature of the relationship between the solvent and the solute is really important to the dissociation of the acid. All right? And I think I've said this before, that when it comes to stuff dissolving, like dissolves like. Polar compounds like to dissolve in polar solvents. So if you try to take a polar compound like hydrochloric acid and stick it into a non-polar benzene solution, it will not dissolve. Okay, part 2, disadvantage here on Arrhenius. He claims that all salts that are produced, you see when an acid and base react, they make a salt, like an ionic compound. Anyway, he claimed that all salts produced in an acid-base neutralization reaction should be neutral, neither acidic or basic. But, as you will soon learn, this is not always the case. For example, if you were to take that hydrochloric acid, which is considered a fairly strong acid, and you react it in equal quantities with ammonia, so like a 1 mole of hydrochloric acid with 1 mole of ammonia, the salt that you make in that reaction actually pulls a pH. So the pH of the end solution in this particular case will be slightly acidic, and Arrhenius didn't have any explanation for this. But there's more disadvantages. Probably the biggest disadvantage, and the one that Arrhenius unfortunately is most infamous for, and caused kind of like commotion in the chemistry world, he proposed the formula of ammonia to be actually ammonium hydroxide. But ammonia is not NH4OH. Ammonia, it was later found out, has a formula of NH3. All right, and we'll talk about how that came about. It's actually kind of interesting. The final disadvantage to Arrhenius's theory is that he thought the H+ ion really truly existed in solution. But that can't be. All right, I want you to think about what a H+ ion actually is. So hydrogen has 1 proton and 1 electron. And when you change the hydrogen into an ion, it will lose its 1 proton and basically become naked, just be a proton sitting out there. Protons are so highly reactive, and it's kind of like if you have a hydrogen ion in solution, everything in that solution is going to find that hydrogen ion because it's sticking out like a sore thumb. It's got a H+, it's positive charged, right? Think about water. Water is polar, and it has a positive end and a negative end. That negative end is going to find that H+ ion in a heartbeat, super fast. So consequently, you should understand that you will never see an H+ ion actually in solution. As soon as H+ comes in contact with water, you're actually going to make this ion. This is called a hydronium ion, and I'll spell that for you. Hydronium. Hydronium ion is just basically a water that has found a hydrogen ion. Hallelujah. So this is kind of interesting. If we actually tried, like seriously tried to get the concentration of the H+ ion in solution, the concentration could be estimated at being 10 to the negative 130th molar. That's just absolutely absurd. What that basically means is that there's no such thing as an H+ ion in water. Bottom line. So obviously the Arrhenius theory is definitely incomplete. We have a lot of issues going on here. So the Arrhenius theory is one of the most limited, kind of closed-minded opinions or theories of acids and bases. They have to have H+ and OH- and in their formula. But, as I'm about to show you, that's not always the case. Along came Bronsted-Lowry. Oh, sorry, typo up here on his name. I do apologize. So Bronsted-Lowry, they were able to kind of evolve the original theory of Arrhenius and kind of refine it. But it didn't happen until 1923, so we actually waited a pretty significant amount of time for a better theory on acids and bases. They define an acid as a hydrogen ion donor. So anything that donates or gives away a hydrogen ion is technically considered an acid. So this particular equation down here represents ammonia dissolving in water. So ammonia will take an H from water. It'll literally, the water will give up the hydrogen ion, it'll donate it and give it to the ammonia. And then I want you to be very careful here. I hope you guys see that double arrow. That means equilibrium. All right, so there is an equilibrium that's happening here between ammonia and water. And so when that hydrogen pops onto ammonia, it turns into ammonium. You see the brackets here? This is the ammonium ion with a positive charge. And then the water that lost the hydrogen turns into the hydroxide ion. You see the OH and there's a minus charge here. But the thing that you have to understand is that by definition, water on the left, you see this guy? water is actually acting like an acid when it gives that hydrogen ion away. And ammonia, according to Bronsted-Lowry, is acting like a base because he accepted that hydrogen ion. So we have completely redefined the whole definition of what an acid or a base is. But that's not all. Remember this double arrow? I want you to pretend for a moment that the reaction is proceeding from the right side to the left side. Let's pretend like this reaction is going backwards. So in the backwards or reverse direction, the ammonium ion will be donating one of his hydrogen ions back to the hydroxide. So in the reverse direction, ammonium behaves as an acid and hydroxide behaves like a base. This right here is the beginning foundation of a concept called conjugate acid-base pairs. Every base has a conjugate acid, and every acid has a conjugate base. The evolution of the theory of an acid-base from Bronsted-Lowry was actually inspired by this demonstration right here. So one of the most famous demonstrations that kind of led to the evolution of the thought of what ammonia actually is came from an experiment of a fusion. On one end of this tube, there is ammonia, and on the other end, there is hydrochloric acid. And when ammonia and hydrochloric acid react together, they produce a precipitate, ammonium chloride. It is a solid. And I want you to notice the placement of where that precipitate is showing up. The numerical values are up on this image up above. So here's a comparison of the distance between the two. And as you know, diffusion rates are somewhat dependent upon molar mass, correct? So if you had thought, like Arrhenius, if you had thought that the formula of ammonia was NH4OH, that would have a very large molar mass, right? Compared to just NH3. So because of this experiment, they were able to estimate that the molar mass could never give us a formula of NH4OH, but instead had to be less than that. So the Bronsted-Lowry definition of an acid and base is probably one of the most important theories for AP Chem. This is probably where we're going to stay around and check things out. In fact, if you look in your book, this is pretty much all section 2 is in chapter 16. All right, so the next theory that we'll talk about kind of moves away from this idea, but I want to make sure you've got some practice thinking about conjugate acids and bases. So remember, like I said, every base has a conjugate acid, and every acid has a conjugate base because of this equilibrium, this dynamic duo, if you will. So every reaction with an acid or a base, I want you to remember that it could be flipped backwards. Okay, every time you think about an acid, I want you to think about the reverse reaction going on. I want you to think about it ionizing and then going back to being unionized. Okay? So an important feature of the Bronsted-Lowry is this relationship between those acids and their conjugate bases and vice versa. So ammonia has a tendency to be kind of weak. It's not a very super strong base. It's not one of the stronger bases. And so this equilibrium sign, you're going to need to start thinking about the reverse reaction going on. So the push, and you guys remember this from kinetics, the push from the forward reaction versus the reverse reaction, you're going to start comparing the strength of both of those arrows, the push, if you will. And if you have a weak base, like ammonia, it's not going to push to the left very well. This equation, this dynamic equilibrium will probably push a little bit stronger to the left, to the reactant side, the way that this is written. And then over here, I think you're familiar with this guy. This is acetic acid. Acetic acid is well known as a fairly weak acid. So again, the push to go to the products is not going to be nearly as strong as the push going the reverse direction. So the strength of an acid or a base kind of helps you determine which side is kind of dominating in this equilibrium. So here's my final thought for Bronsted-Lowry acid-base theory. Since protons are always transferred in the Arrhenius concept, here's just something you should consider. All Arrhenius acid bases are also Bronsted-Lowry acid bases. But if water is not involved, like with hydrochloric acid and ammonia, you're gonna have to lean over to the Bronsted-Lowry concept and not Arrhenius. So Bronsted-Lowry explains Arrhenius to include any proton transfer. Water, not a requirement. Okay, water is not a requirement for an acid-base reaction for the Bronsted-Lowry. So the final theory that we want to talk about is Lewis acids and bases. And I think this is so interesting. You may probably not know this, but certain metals on the periodic table, if they dissolve in water, like heavy metals, certain metals, when they dissolve in water, they can actually change the pH of the water solution. So keep in mind that metals don't have any hydrogens at all. So now where do we go with this? You have to rely on some of the information that you received from intermolecular forces. The aluminum ion has lost 3 electrons, and it is fairly small, but that charge is sticking out like a sore thumb. So the polar water molecule is going to want to have a tendency to push its negative charge to compensate for that positive charge sticking out like that. So what I think is interesting is that you can dissolve pure, like these metals, you can just dissolve them into water and get a pH because of the strength of those intermolecular forces. So we have to have a new theory. It becomes this: acids is any substance that can accept a pair of electrons, and a base is any substance that donates a pair of electrons to make a new bond. So for example here, hydrogen ion, copper 2 ion, and aluminum ion, all of these guys are electron poor, or electron deficient, if you will. And so they have a very high potential to accept a pair of electrons from something or anything around or near it. And if that happens to be water with, you know, a negative side on there, like maybe a polar compound, it is going to try to grab on to that oxygen. Now, keep in mind, if it grabs onto the oxygen, that's going to expose your hydrogen ions. Am I right? And if you are exposing hydrogen ions, if you've made the hydrogen ions exposed in any way, you're actually creating an acid. Acids make hydrogen ions in solution. Remember that? That was like the basic definition of an acid or a base. So it makes sense then that these species, if they're ripping away the electrons and kind of being attracted towards those negative electrons on the oxygen, those hydrogens are going to start sticking out. And if those hydrogens stick out, you've made an acid. We'll get more into detail about this particular slide a little bit later on, especially in section 5. But I think you might be able to kind of recognize that every acid has a conjugate base, right? So, for example, I don't know if you can see this very well, but at the very top you have hydrochloric acid. When hydrochloric acid does its thing and it donates its hydrogen ion, on the other side of the equilibrium, you're going to be left with this guy, the chloride ion, right? So what I think is interesting is hydrochloric acid is a fairly strong acid, and when it lets go of its hydrogen ion, you're going to be left with the Cl, like kind of like a spectator ion just kind of sitting around in the product side. So if there's any way to think of acid coming back in the opposite direction, remember I told you start thinking about the opposite direction, the chloride ion has very little push. So I want you to notice that hydrochloric acid is on the scale up high as a very strong acid. But your chloride ion, you see right here, it is a weak base. It's not going to be able to grab onto very many hydrogen ions. It doesn't have any strength, if you will, to push the equilibrium back over to the reactant side. Because hydrochloric acid is like, booyah, pushing you to the products. But chloride is going to be opposite, the chloride ion. So strong acids make weak conjugate bases, and strong bases make weak conjugate acids. So they're always kind of equal and opposite. So we're moving on now into section 3 of your book, autoionization of water. So as you have seen, water is amorphic. It can work both as an acid and as a base. That's interesting, huh? So what I think is interesting is in pure water, a few, and I do literally mean a few, very small amount of water molecules will act as bases and a few will act as acids. So what I think is kind of neat is that two water molecules that are side by side, if they hit each other in just the right way, think about kinetics, if they hit each other in just the right way, it will actually produce the hydronium ion and the hydroxide ion. And it'll do this in any particular setting. Doesn't really matter. You don't have to like push the water to do anything. You don't have to shake it or anything. This phenomenon is referred to as the autoionization of water. And it is from this phenomenon that we have developed a very strong kind of theory about pH. So this is kind of going to walk us into how did we get the pH scale. So if you look at that reaction I just showed you, the autoionization of water, the equilibrium expression for that particular process is the K sub C. So this is a special equilibrium constant. This is the ion product constant, is equal to the H3O plus ion, that's a hydronium ion concentration, multiplied by the hydroxide ion concentration. This is a very special equilibrium constant. It's known as the ion product. You notice it's products, right? It's the ion product constant. So you'll notice like back over here, the H3O and the OH, those are products, right? So we call it the ion product constant. And for water, if it's specific to water, now it could be any ionic compound or any acid or base, but if we're talking about water, we give it even an extra special symbol. We call it K sub W, W for water, okay? At 25 degrees Celsius, water will have a ion product constant of 1.0 times 10 to the negative 14. What does that even mean? So this guy's value, it actually has a numerical value if we're talking about water. It has a numerical value of 1.0 times 10 to the negative 14. Do you know what each of these values would actually be? In other words, can you solve for those values? Now, if you think about it, the products have a 1-to-1 mole ratio, right? So then their two values should be identical. It would be like x times x, or if you want, just like x squared. What is the value of x? In any sample of water, the hydronium and hydroxide ion concentration, as long as it's pure water, it's at 25 degrees Celsius, each one of these guys will have a concentration of 1 times 10 to the negative 7 molar. And you'll notice that since they are both in a 1-to-1 mole ratio, they're both equal. So the molarity of the H3O plus, which kind of behaves like an acid, we've kind of described that before, and the OH, if they're identical, if their molarities are identical, then they are neutral. You see what I mean? They're neutral. If both of those quantities are the same, the substance is neutral. So when you think about those concentrations, they're fairly low, like 1.0 times 10 to the negative 7th, right? We created from that relationship from water, we created a scale of these negative powers of 10. And in order, I don't know if you know very much about how log works, but this is log base 10. And it works with powers of 10, like scientific notation, if you will. So if we were to create a formula to determine how much hydrogen there is, we use the terminology pH. So pH is going to determine how many hydrogen ions they are. It's kind of like a numerical value for the concentration of H's, or the acidity. So when you do negative log, and let's pretend you stick in here 1 times 10 to the negative 7, you will get a pH of 7, and that is how logs work. So another way to think about this is to consider the fact that K sub W is the hydrogen and the hydroxide multiplied together, and it'll give you a value of 1.0 times 10 to the negative 14. So since in pure water your H3O plus is equal to your OH minus, you're going to get this value for your concentration. So instead of looking at concentration like that in scientific notation, the pH scale sure does make that a little bit easier to see. It is a purely numerical value that represents kind of the power of 10, the molarity, if you will. So here are some very, very important relationships to understand. 1.0 times 10 to the negative 14 will be equal to your H plus ion concentration times your OH minus concentration. And that's true for pretty much any acid or base. So we can compare the H plus and the OH minus. And also, if you rearrange this formula, you can actually solve for your H plus ion and your OH ion concentration. Now, understand, when I say H plus, you guys know that I'm also talking, think about like Arrhenius and Brownstein-Lowry, that whole lecture about that. We're really kind of talking about the H3O plus, the hydronium ion. So you might see H plus, you might see H3O plus, and just realize that those are the same things, okay? So here's a great picture that I've used in years past, and it kind of helps you to think about how acid-base relationships work. So if you have the pH, you can switch all the way around to OH ion concentration, but you're going to have to follow one of the paths. So if you go back and you think about how pH works, pH is equal to negative log concentration H plus, right? Could you actually rearrange this to go from, say, for example, like, do you know what the opposite of log is? What the opposite of log is? Log is like base 10, right? So if you have the pH, you can actually do something like this. To get rid of log, you're going to do a 10 to the log, right? You're going to do 10 to the x. That's what the opposite of log is. So if I get rid of log, that'll get rid of this bad boy. This will give me 10 to the concentration of, This will just give me concentration H. But over here, you want to carry over the negative sign. Okay, get rid of that. And what that'll do is that'll do 10 to the negative pH. So in other words, if you were to take the number 10 and raise it to the negative pH, that should give you your hydrogen ion concentration. And so that's what you're seeing over here. I've got some formulas stuck in here. You see that? Okay, and then this is what you're familiar with. This is the dissociation constant for water. And then you divide it here by your OH, and that'll give you H plus. Okay, make sure you kind of remember this, please. This is super important in this unit, and it'll save your butt. So there's other P scales, okay? The P in pH tells us to take the negative base 10 logarithm of that quantity. But there's some similar, there's some other pHs. There's a POH, which is the exact opposite of pH. If pH measures the strength of acids, POH is going to measure the strength of bases. So, for example, your pH scale goes from 1 to 14. This is your pH. Low pH means that you have a very strong or very high amount of hydrogen ions. So this is your acid, right? And then a pH of 14 would mean that you have very low H pluses, and so therefore you've got a pretty strong base. But if I flip that and we talk about the POH scale, the POH also runs from 1 to 14. But this time, if you have a POH of 1, remember that's the strength of a base. So that would mean that you have a really strong base down here, right? 10 to the negative 1 versus 10 to the negative 14. It's not very much OH, huh? So that would actually give you an acid. So there's an inverse relationship between acid and base concentrations. And another thing to keep in mind is that since we've been talking a little bit about kW, you know how kW has that scientific notation 10 to the negative 14, right? So something to keep in mind is that your negative pKw is going to be equal to negative log kW. Good relationships, good formulas. Make sure you got them written down and memorize them. So let's watch this. Because your hydronium times hydroxide is going to give you, those concentrations is going to give you 1.0 times 10 to the negative 14. We also know, therefore, that if you were to take the negative log of the hydronium and you add it to the negative log of the hydroxide, you should get the negative log of your kW, which is 14. In other words, what we're trying to tell you is that if you take your pH and you add your POH, you will get 14. So pH plus POH is 14. Acids and bases are linked. Conjugate acid bases are also linked. Here are some good examples. Indicate whether solutions with each of the following ion concentrations are neutral, acidic, or basic, and what their pHs are. So in this first case, you have a hydrogen ion. That's important to make sure you determine if it's hydrogen or hydroxide. So in order to get your pH, you're going to do negative log of that number. So get your calculator. Now, whatever number you get, remember, if it's less than 7, it's an acid. If it's greater than 7, it's going to be a base. I got about 8.4, so technically A would be basic. So I do want to talk a little bit though about C. You need to remember in C that this number right here, this value for the molarity, represents the hydroxide ion concentration. And if I just kind of look at this, and I'm trying to teach you guys just how to look at things and kind of figure them out, if your hydroxide ion concentration is that low, that's pretty low. Look at that, it's like negative 13. I'm going to anticipate that this particular guy is actually an acid. Go ahead and go through and do your math and check to see if I'm right. This final sample problem, I would like you guys to try by yourselves, so I'm actually not going to give you the answer here. It's in your guided notes. See if you can do it, and then when you guys come back next class, if you have a question, you can always ask. All right, guys, that is the end of this lecture series. I hope it is helpful. Best of luck. Until next time.